Okay, today we're going to be thinking about a couple of other circle theorems. Okay, so the next theorem we're going to be doing is one which we have a circle, and in our circle we have a quadrilateral. So this quadrilateral can be thought of, we've got the points A and B, and we've got an angle subtended between the opposite segments here, but we've also got another angle subtended by the opposite segments here. And this theorem states that this angle plus added to this angle equals 180. So if we call this angle P, and this little p and little q plus little q is going to add up to 180. So let's now consider the proof for this. Let's redraw this without all the details for our proof. Okay, we've got point A, point B, point P, and point Q. Now I'm going to draw another circle because I want to make something clear, and I'm going to put in the details for this part of our diagram in Q. So here's our proof. So we know that I'm going to draw a dotted line for our chord here, and our origin was up here, and we know from our previous theorem that if we were to call this angle here P, we know that this angle here would be 2P. Now, I've missed out the top part in this circle. Now we put our origin in. That's too high up. What about here? So here's our origin, and we've still got, if we still think of the chord here, this is we still have this this angle here. It takes us to the origin from A and B, but here we're dealing with this angle here, Q. So now 2Q is here, because the arc that we're dealing with between A and B is still the same arc. It's still the same arc that we're dealing with as we were dealing with here. So it's 2Q up here. So we can now think of this, put it in here, this is Q, this will be 2Q. So the angles at the centre are twice, that is 2P and 2Q. Now round the origin, the angle is angles at the origin add up to a 360, because we've got a circle around here. So 2Q plus 2P must equal 180. So 2P plus P must equal 180. Oh, 300, sorry, 360. Sorry. 360. So P plus Q must equal 180. So we've shown that this angle added to that angle has to always add up to 180. Now, when I first started, I said we're basically drawing a quadrilateral inside our shape. So we can this theorem can be rewritten as, we can think of this quadrilateral as a cyclic quadrilateral, because a quadrilateral inside a circle. And points A, P, B and Q, because they form a quadrilateral, we can say opposite angles of a cyclic quadrilateral add up to 180 degrees. So this angle here and this angle here will also add up to 180. So let's look at an example using this theorem. So find the angles X and Y. So let us draw what we're dealing with. And we'll draw another circle here, draw a bit higher up. And so we've got a quadrilateral, so it's going to be a cyclic quadrilateral. And here, this one starts with the origin. And it goes down to here. So in this one, our origin is here, and this is angle X, and this is 116 degrees. And here, this is angle Y, up there, and this is 96 degrees. So for angle X, we know X plus 116 must equal 180. So we can just write a wee explanation, because the angles are in opposite segments. Or you could also say opposite angles of a cyclic quadrilateral add up to 180 degrees. Either explanation would work. So doing the arithmetic, which is pretty simple, you're going to take 180 to take away 116. X is going to be 64 degrees. Now, Y, for angle Y, two construction lines are needed. So what I'm going to do is let's add this here to make our quadrilateral. So now we need to get A. So we know that 180, I'll explain why we're getting A in a minute. 180 plus 96, oh sorry, scrap that. A plus 96 must equal 180, so A must be 84. Now, the reason we've done this is, if you see here, we've got our 2 points here leading up to A. We know when we've got an angle up here, the angle that meets at the origin, this is the origin, here is going to be 2A. So Y must equal 2A, which is going to be 168. So we've taken the two theorems and we've brought them together to help us solve this problem. Now, we're going to look at another theorem. So let's get another circle. That's too high up. Oh, that's far too small. So this theorem involves tangents, and so we've got a tangent here and chords. And so we've got a tangent and we've got a chord. And now, so this is a chord, and now we're going to project up to get the angle subtended in by the chord. So this is the theorem. We've got here, I'm going to change the colour so that we can, so it'll show up better what we're dealing with. So the angle from the chord, let's get the pencil. So the angle from the chord here down to the tangent is equal to the angle subtended in the opposite segment. Oh, we've done it far too far, never mind. So let's write that down. The angle between between a tangent and chord is equal to the angle subtended in the opposite segment. This is called, so this is often called the alternate segment theorem. So, the proof. Let's draw another wee diagram, because we're going to think of sometimes when you want to prove something in mathematics, you look at a special case, and then from that special case you can then generalise to all cases, and that's exactly what we're going to do here. So we're looking at the special case where we've got the tangent and it meets at the diameter. So here's the diameter. So that is at 90 degrees to that. And then we're going to have our chord here. And I should have made this a bit bigger. So we're going to call this angle here, well, x. We're going to call this angle here z, and we're going to call this angle here y. So what we're trying to prove is x and y are the same. So, since the angle is the angle in the semicircle is 90 degrees, y plus z must equal 90 degrees. Previously on a previous video we talked about this special case where that's going to be right angles. So y plus z must equal 90 degrees. Since a radius and tangent meet at 90 degrees, so this has to be 90 degrees, z plus x must equal 90 degrees. Therefore, y plus z must equal z plus x, which means y must equal x. So that's in this special case. But how do we know this is true for all cases? Well, we know that, I'm going to change my colour to make this show up. We know that from our previous theorem, if we've got our chord between this point here and this point here, that this angle must, get rid of that, this angle here must be y. That any angle subtended in opposite segment, the angle must be the same. Let's get rid of that. So we've just moved this point here to point Q. We'll call this point Q. So it's no longer, this point here is no longer on the diameter. But this angle here, so the angle with the chord here, must still be, x must still be the same as y. So the angle at Q is equal to, we'll call this point here P, not sure very well, to the angle at P as they are angles in the same segment. Thus, the theorem is proved. So I hope that helps.